Alrighty, so today we're going to be looking at liquid rope coiling, and we have two liquids here to demonstrate it. The first one is milk, and the second one we're going to look at honey and see what it does. So for the milk, we have a little glass of milk, and we also have milk and champagne in a champagne glass. And we're going to dump the milk on top of this milk and see what happens. Alrighty. So there's the milk. And now for the honey, we have a honey stick, so we're going to dip the honey into the honey stick and then bring the cup down and see what happens. Wow. Would you look at that? That's pretty neat. What you see here is a slow motion video of the liquid rope coiling effect with honey. The coiling of a thin rope of viscous fluid falling from a sufficient height onto a surface is a common fluid dynamical instability that occurs in situations ranging from food processing to lava flows. And the history of the investigation spans for nearly 50 years. So people have been studying the liquid rope coiling effect for about 50 years. And what we've found out is that there are a few different factors that contribute to the rope coiling effect. These factors include the density of the fluid, the surface tension coefficient, and the kinematic viscosity of the fluid. Here's a drawing of the liquid rope coiling effect as we just saw with the honey. Now there's a couple of variables to take into account when thinking about the mathematical side of the liquid rope coiling effect. So here we have the coil, and here we have the tail up top, and together those make up the height, h. Now we also have the mass flow rate, which is q, and the upper radius, or the radius of the tail end of the honey, and that is a sub 0. And then the lower radius of this honey right here down in this section is a sub 1. And now what's really cool about this is the angular coiling frequency, and that is the speed at which the honey will coil. Alrighty, so what we have here are the 4 different kinds of flow that scientists can describe after studying this phenomenon for 50 plus years using the variables that we've just previously discussed. So the first one is the viscous regime, and this is where the height is relatively small and the fluid basically has to get out of the way of itself. And that is what causes the rope coiling effect. And then here's the equation to find the angular coiling frequency. The next one is called the gravitational regime, and this is where it's a little bit higher than the viscous regime, and it's where gravity takes over as the height increases, which stretches the fluid. And now, as you noticed in the first equation, there was no viscosity. And as we come into the gravitational regime, viscosity is introduced because it resists the stretching. Now the third one is when h gets very large, and basically the rope, or the radius of the rope, is very, very small. And here's the equation shown to find the angular coiling frequency, which is very, very fast. And as you can see, the radius, the lower radius, is raised to the 10th power, which would make this number larger, which makes sense. And then the last one is called the inertial gravitational regime. And this happens somewhere between the gravitational regime and the inertial regime. And basically, everything that we've discussed goes out the window, and scientists aren't sure why it does this. And what happens is, instead of a constant coiling frequency of the honey or the liquid, you get a strange figure 8 pattern, and there isn't really an equation to define what happens. Alrighty guys, thanks for watching. Hopefully you learned a little bit more about fluids and the liquid rope coiling effect with honey. Pretty neat.